Hi and welcome to this next lecture on machine learning. In this session we will discuss some more unsupervised learning methodologies. Before we delve into clustering, we will discuss generative models, which are foundationally important to understanding clustering and EM algorithm. Generative models can also be used for classification, as we will see next. The difference between discriminative and generative classification models is that discriminative models, they directly model the class posterior given the query point or the data instance. So far most models we have discussed are discriminative in nature. With generative models you could also model the probability of the data point itself independent of the class. In fact, mixture models do that. Coming back to generative models for classification, the idea is to obtain the posterior using the Bayes rule. So the probability of the class being, say, Zi given the data point phi x could be obtained by multiplying the probability of generating the point from the class Zi in the first place times the probability of the class Zi divided by the probability of phi x. Now the probability of phi x itself could be obtained through marginalization. It is a sum over all the possible labels of probability of phi x given ZL of probability of ZL. So what generative models give you through the probability of phi x given Zi is how likely is point phi x given the class Ci. On the other hand, discriminative models directly model the probability of the class given the query point. In the rest of the discussion we will use Ci and Zi interchangeably. Now an unnecessary overhead is incurred through this denominator in the posterior. This denominator is basically trying to account for the probability of phi x. However, if you are interested in finding the most probable class through an argmax, let us say an argmax over I, you do not really care for this denominator. So you could actually ignore the denominator because it is anyways independent of the class I. The probability of a point given Zi or Ci could be modeled based on whether the attributes are continuous or discrete. In the continuous case, a very often used model is the multivariate Gaussian or multivariate normal distribution. For the ith class, you model the mean and the covariance matrices to be mu I and sigma I respectively. This leads to a classifier called the Gaussian discriminant analysis based classifier. Your attributes could also be discrete, in which case you could resort to Bernoulli or multivariate Bernoulli models for each feature, and assuming that the features are independent you get something called the naive Bayes classifier. So in general you get the posterior using Bayes rule, and to find the most probable class you look at argmax over I of the probability of Ci given phi x, and that is nothing but the argmax over I of probability of phi x given Ci into the probability of Ci. So what matters on the right hand side is the probability of generating the point from that class and the probability of the class itself. Probability of class Ci is also called the class prior. So classes which have very high prior could start dominating the argmax, and that is often a problem with generative models for classification. Let us consider this Gaussian discriminant analysis as a canonical example of generative models. So for every class Ci, we will have a multivariate normal distribution centered around the vector mu I with covariance matrix sigma I, and we will assume that each data point phi x is generated using exactly one of the multivariate normal distributions. Now let us try and understand what the separating surface, the decision surface, will look like. It turns out that the decision surface will be quadratic, especially when the covariance matrices are not constrained to be the same. This classifier is also therefore called the quadratic discriminant analysis classifier. Here's how the model would look like. So let's say the ellipsoid for the positive class look like this, and that for the negative class with the 99 percentile area look like this. What we expect is the separating surface to be pushed away from the green ellipsoid and pushed towards the red ellipsoid. Both ellipsoids are kind of 99% percentile regions, and therefore the separating surface would look like this, a quadratic surface. On the other hand, if the ellipsoids had the same covariance but were just shifted by virtue of the mean vector, you would expect the separating surface to be linear. So analytically, let us see why we would get a quadratic separating surface. So separating surface should be such that the probability of class 1 given phi x should be the same as the probability of class 2 given phi x, and that would mean that the product of the probability of generation of the point from class C1 times the probability of class C1 should equal the product of the probability of generation of the point from class C2 times the probability of class C2. Now this would mean that even with logs you should have equality, so which means log of probability of phi x given C1 plus the log of probability of C1 should equal the log of probability of phi x given C2 plus the log of probability of C2. And now several of the terms here, both in the log of the probability of point given the class and the log of the class prior, are independent of phi x. What we are interested in is in showing that the separating surface is quadratic in the phi x space. So what we will be interested in is restructuring this equality so that the terms not involving phi x are on one side almost all the terms not involving phi x. So the terms that we can readily identify are log of probability of C1 and C2. In addition, what will going to be is the log of these terms which are independent of phi x. What remain include the log of the exp, so this will mean just the exponent, or these terms. So writing them down, we will basically get minus of phi x minus mu 1 transpose sigma 1 inverse phi x minus mu 1, this quadratic expression, plus phi x minus mu 2 transpose sigma 2 inverse phi x minus mu 2. This term on the left hand side cannot be significantly simplified, and even after simplification, as long as sigma 1 does not equal sigma 2, it will remain quadratic in phi x. Thus overall you would expect the separating surface to be quadratic. So we get this equation which is quadratic in phi x. What about maximum likelihood estimates for quadratic discriminant analysis? Well, we should be able to quickly build upon parameter estimation for a single Gaussian. In fact, this is quite characteristic of generative models, where you are looking at the probability of generation of point for the class 1 independent of the probability of generation of point from class 2. So let us say we had M2 negative examples coming from a distribution with mean mu2 and covariance sigma 2. We are interested in their maximum likelihood estimates mu2 hat and sigma 2 hat respectively. Likewise, let us say we had M1 points from the positive class characterized by mu1 and sigma 1 parameters. We are interested in their estimates mu1 hat and sigma 1 hat. One can get these estimates in the maximum likelihood sense by setting the log likelihoods to 0, but intuitively, since the estimation is done separately for each class, you would expect mu1 hat or mu I hat in general to be the average of the feature vectors of points that belong to that class. So this is nothing but summation over all the points x belonging to class Ci of phi of x averaged over all the points in that class, which means we divide by 1 by mi. Likewise, the covariance matrix estimate is going to be the average of all the rank 1 covariances evaluated at individual points in the class Ci, but this rank 1 covariance is obtained using the maximum likelihood estimate itself. So this will be phi x minus mu I hat phi x minus mu I hat transpose. This is an n by n rank 1 matrix. A third term that is specific to use of generative models for classification is that of the prior. The class prior has a maximum likelihood estimate which basically is a fraction of points that belong to that class. Also, we note that the maximum likelihood estimator mu I hat turns out to have a multivariate normal distribution itself, and since the expected value of this estimator is the actual true value, mu I hat is also called an unbiased estimator. It turns out that sigma I hat is not an unbiased estimator. A very interesting special case is that of the Nye-Bayes classifier, Nye-Bayes classifier for Gaussians is nothing but the Gaussian discriminant analysis with a restricted setting, the restriction being that each of the sigma i's is assumed to be diagonal. So a diagonal matrix sigma I will mean that the features are independent of each other given the class. One can also look at the maximum a posteriori estimates. This is simply extending the analysis that was already presented for the single class case. All you do now is estimate the sigma I and the mu I after having made mi observations in class Ci. As before, the class prior is just the fraction of points belonging to that class. One could also resort to some sort of smoothing on the class prior through regularization. As part of the tutorial, you could look at a very special case of Gaussian discriminant analysis where the covariance matrices are constrained to be shared. So you have a single shared covariance matrix. Well, what does this mean? You could have the following case. You could have the positive points and negative points with similar shapes but shifted in their means. The claim is that the maximum likelihood estimates are very similar, with the difference that the covariance matrix is now computed across all the points but with respect to the corresponding means. Now also it turns out that the separating surface with a shared covariance will always turn out to be linear. As already discussed in the case of quadratic separation, the non-linearity was primarily because of different covariances which pushed the separating surface in different directions at different points. Well, that won't happen if the covariances are shared. As part of the tutorial, you can try and prove this analytically, and it's very intuitive that when covariances are shared in the quadratic expression, the terms involving phi x transpose sigma inverse phi x will basically cancel out, and all you will be left with is the linear term. So this is how you will get linear separation with linear discriminant analysis. Now let us look at a slightly non-trivial case. We have so far assumed that each phi x is generated using exactly one of the multivariate Gaussians. There could be two exceptions to this. One is the exactly one assumption can be generalized to say k. So the violation could be because phi x could have been generated from multiple classes. I will provide you with some extra notes that deal with what to do in the case when phi x could be generated from multiple classes, and this is more generally called the multi-label problem. It's a multi-class and multi-label problem. And an even more serious violation is when this exact is violated, which means nobody is able to identify for you which are the classes the points belong to. This could very well be the case if you were provided only the points without their labels. What you note in this figure is while the labels are not provided, we are very much tempted to identify two classes or clusters. So there are two potential clusters, but the characterization of the problem is that membership of the points phi x to different Ci's is unknown. So in the case that the membership of an example of different classes is unknown, we could actually look at the probability of a point as the probability of the point comma the class pair, but marginalized across all classes. Now we will refer to these classes as clusters because the labels are not to be provided. One could of course simplify this expression. So this expression can be written using the Bayes rule as the probability of phi x given the class Zi or the cluster Zi times the probability of the cluster Zi. For example, the probability of generating a point from a cluster could still be determined by multivariate normal, that is what we see here. The class priors which continue remaining unknown and to be estimated are now related to the coherence of points within a cluster. So the probability of a cluster is not predetermined just by the number of points belonging to that cluster. So in general, one could have an unsupervised mixture. You have a multinomial variable z which indicates a mixture component that a point belongs to, and by all means a point can belong to all the mixture components but to different degrees. So let us say the probability of generating a point phi x from the ith cluster is given by the density function fi x with parameter theta I, and then the finite mixture model is defined as the probability of phi x being modeled as sum over all the hidden clusters of the prior probability of the cluster times the density function based on that cluster. We will also adopt a compact notation for the prior probability of a cluster and call it pi I. So we have these mixture components or mixture weights pi 1 to pi k and parameters for each of those mixture components theta 1 to theta k. Specific example of the mixture model is when the probability of generation of a point from a cluster is the multivariate normal distribution. In the supervised setting, we were able to learn the mu i's and the sigma i's using either maximum likelihood or map estimate. This was because a unique z was obtained for any x. In the unsupervised setting, we need to learn these parameters in the presence of incomplete data, which means we have only access to instances phi x. At best, we may be told the number of clusters, and with this minimal information we need to estimate the following. We need to estimate the parameters theta I of the different mixture components. This could mean mu I and sigma I in the case of multivariate Gaussian. We also need pi I, the prior probability of a class. So let us try and do this. We write down the log likelihood which is supposed to be the sum over all the points of the probability of those points. Now we do not have the class label, but what we do here is express this probability of data point using the mixture model, and this mixture model has a summation. The summation is over all the possible latent classes or clusters. Now the log likelihood has to be maximized, and in general we are interested in the parameters pi and theta. Specifically for mixture of Gaussians, we are interested in pi, mu and sigma. Now what is a problem with this setting? So recall that when we were dealing with generative models or even with discriminative models, we were often encountered with summation over log. The summation over log was nothing but log of the product. In fact, we often got to the summation of log from the log of product over the different examples. This primarily results from the IID assumption on the data points. So in the general setting, we could actually bring a product outside the log. However, how do you deal with a summation sitting inside the log? So log of summation, what can we say about this? We recall that the log function looks concave. So log function could be like this, and concavity basically means that if you draw a line segment connecting any 2 points, then all the points on this line segment will lie below the points on the curve. Now what does this below translate into? Well, it basically means that the function applied to a convex combination of points will be greater than equal to, will lie above the convex combination of the function applied at those points. Specifically, since log is known to be concave and not just concave, it is strictly concave, we would have that log of some summation of convex combinations should be greater than equal to the summation of log. So at best we could apply some inequality like this. In fact, it will be this inequality that will give us expectation maximization algorithm. What we will do now is present a very simple and intuitive procedure to solve this problem. So since log cannot be distributed over summation, we present an intuitive and iterative approach to solving this problem. Now, is this approach going to give us the right solution, a unique solution, and so on? Well, for that we will need to understand more of the concave inequality, the lower bound that was obtained by virtue of concavity. We will need to understand the general EM algorithm setup. We will first look at an intuitive approach which is iterative. So let us do the following. Let us consider the maximization of the summation of the log of the summation, and let us write down the necessary optimality condition for this maximization problem. What we do here is we will set the gradient with respect to each of the mu i's to 0. Mu I, recall, is a vector. So the outer summation will remain as it is. We have log of a factor which involves mu I. So by chain rule we would first have 1 divided by the factor that sits inside log. Thereafter only that term in the summation which involves the ith index will stay. So what that means is we will next by chain rule multiply with pi I. How about the derivative, the gradient for the normal distribution? The normal distribution is e raised to quadratic expression. The derivative of e raised to x is e raised to x. So we will have the normal distribution including the exponentiated term and multipliers remain as they are for the ith cluster. So this is n of phi xj mu I comma sigma I. Finally what we will have is the derivative for the exponent. So third component we are interested in is this minus of phi xj minus mu I transpose sigma I inverse phi xj minus mu I. So taking the gradient we will basically have the last two terms, which means sigma I inverse phi of xj minus mu I. This whole thing will need to go to 0. So the first thing we note hereafter is that the sigma I inverse can actually come out all the way. It is because index I does not depend on the example, and then we note that in this expression involving a matrix sigma I inverse with some vector b, the sigma I inverse is non-singular, and so what we require therefore is the remaining expression the vector b to go to 0. And what is that remaining expression? Well, the remaining expression is everything except sigma I inverse. So here is our remaining expression, this is the vector b, it should go to 0. Now this involves mu I in extremely complex ways, so there is no clean way to solve this in closed form to get an estimate for mu I. What we will do is resort to the so called EM trick. We make the following observation: the expression sitting here is nothing but the posterior distribution for the ith cluster given the data point xj. What we do is pretend that this expression, this posterior, is independent of mu I and sigma I. In fact we obtained this from a previous iteration, so called E step or the expectation step. Pretending this to be independent of mu I and sigma I, which is not actually the case but is a trick that is employed in an iterative setup, we then try and solve the remaining expression. What will that amount to? Well, we need summation j equals 1 to m of the probability of zi given phi xj times phi of xj minus mu I to go to 0. Now this basically means that mu I or its estimate is a weighted combination of the phi xj's where the weight comes from probability of the ith cluster given the point xj. There is a normalization involving summation over all these memberships. So here is where we are. We have the so called M step in which we have obtained mu I as a weighted combination of the phi's, and the weights are basically coming from memberships that were obtained in another iteration. Using this membership, we then estimate the weighted linear combination of all feature vectors, which is feature vectors across all points, weighted by membership of the point in Zi. You might want to recall what the expressions were, the estimates were in the case of simple Gaussian discriminant analysis. In the case of Gaussian discriminant analysis, you were given the membership of points to clusters or classes, so effectively for any point that belonged to this blue cluster, we knew that the probability of Z2, let us say Z2 is a blue cluster, given point phi x is 1, and likewise for the red one we knew that the probability of Z1 given phi x was 1. Here we have continuous memberships, every point can belong to every cluster because we do not know the colors blue and red. What were our M steps like? Our mu I was the average of feature vectors for points belonging to that class Ci. So let us note the contrast. First of all, we have hard membership earlier which was known by virtue of the training data. Our membership now is soft, every point can belong to every cluster. As a result, when we deal with the parameter estimates, we now consider contribution from all points based on their membership. Earlier, the membership was equal across all points that belong to that cluster. We will now need to apply the same trick for estimating the parameters pi I and sigma I, and in all cases we will consider variations of the Gaussian discriminant analysis estimates, but using the weights which correspond to the membership of points to clusters. So here are the M step estimates for mu I, which we already seen. Sigma I, it's very similar to that for Gaussian discriminant analysis, but in the case of Gaussian discriminant analysis we just had 1 upon mi instead of these weights. Likewise, pi I was earlier the probability of class Ci, and that was just mi divided by m. Now what we have is the membership of every point to the ith class being accounted for. The E step is basically use of the Bayes rule. It basically corresponds to what we substituted as a constant for that particular iteration, the membership of the jth point to the ith class. Now these in turn are obtained from the parameters from the previous iterate. So the pi I, the mu I and sigma I are from the previous iterate. Maximization step also has the name M step. Let's understand this with an example. To begin with, we initialize all the parameter weights. So we initialize the mu's for each class, the sigmas for each class, and this is basically step number 1. Step number 2, we start looking at the membership of these green points to the initialized clusters in blue and red. The clusters don't change. What changes here in the E step are the memberships. And these memberships have been indicated in different shades of blue and red respectively in the second plot. The third plot, you re-estimate the cluster parameters. This is the M step. So what we do here is compute for each cluster I, mu I, sigma I, and now also pi I, and therefore the shapes have changed, the positions have changed. Step 4, like before, is the E step, which doesn't change the ellipsoids as such, but you re-estimate memberships. So what changes here are the shades which indicate the memberships. 5, you again perform an M step, re-estimate the parameters mu I for each class, sigma I and pi I, and so on. You keep doing this till you find that the parameters have converged. So apparently by the 6th step, parameters seem to have converged. In fact, parameters and memberships both seem to have converged. In the next session, we will generalize the EM algorithm beyond Gaussian mixture models and then revisit Gaussian mixture model as a very special case of the EM algorithm. Thank you.